Welcome. In this little tutorial, I'm going to show you how to build a language in MPS. We'll build a little state machine language with events, variables, states, transitions, and guard conditions by reusing an existing expression language. We'll also build a second language that tests the original state machine language, and we can even run this to execute the tests. Finally, we conclude by illustrating how to build tabular notations and diagrams as part of the overall state machine story.
So in the next step, we are going to integrate expressions into the state machine, so we can do something like this, where we write that for example, this transition only fires if this event occurs, of course, but then if this variable counter is greater than 0. And we do that by using an existing expression language called KernelF. It's basically a functional programming language. If you want to learn more about it, you might want to check out this booklet or 100-page paper about the language. But I'll give you a brief overview about it here before we then integrate this language into the state machine. So basically, you can write expressions. And for example, you can add two numbers, right? You can compare things. You can define functions, whatever. And then return I plus j, right? Now it complains here that int shouldn't be used because in fact there is a number type which even lets you do range specifications, right? So if we do it this way, then we can try to see what is the type of this, and it's a number between 10 and 30 because the type system to some degree does range checking for numbers, and it knows that if you add 0 to 10 with 10 to 20, then the result must be between 10 and 30. And of course, if you now do something like 100 plus add 5,50, well, the first thing you get here is an error because it's not between 10 and 20, so let's do 15. And then we can ask the type system, what's the type of this? Well, it's a number between 110 and 130. And you can obviously see the system supports type inference because you can ask the type of this. It's again this number between 10 and 30. And so then you never specify the type explicitly here, but you can, right? You can have the system derive the type and write it down explicitly. And you could do the same thing here. For example, you can say it's a number, any number, between 0 and infinity. And of course then, because this one is between 110 and 130, that's a subtype, so that works. If you try to add a string, of course it doesn't work. So it's a full-blown expression language which you can use for expressing all kinds of things, right? For example, you could define values. Let's, for example, call it counter, and then another one, and say, is the counter greater than 0, right? And this, of course, then is a Boolean because it's a comparison. And of course, this is exactly the kind of thing we do here, except that counter here is not a reference to this global value, but in fact, it is a reference to this variable inside a state machine. We'll get back to that. Now, what KernelF also has is an interpreter. So there is a little support for testing, so we can test adding. And we can make this examples thing visible here, right? So then we can ask assert the counter, right? We see that now because it's visible because I've imported this thing, is 0, and I can run this, and it's green because in fact counter is 0. We can look at the x from before. Let's say it's 0. Of course it's not. So we get an error, expected 0, but was 119, right? So it's 119. You might wonder, how do we know it's 119, right? Let's start the debugger, and we can now look into the evaluation tree, and we can basically see that the value is, it adds 100 plus 19, because adding 4 and 15 is 19. We can jump into that thing. And so basically this is a full functional programming language. Again, I'm not gonna go into too many details. You can see them from this paper, the features it supports. But what is interesting is some degree of implementation here, right? So for example, everything is basically an expression. So this one is a constant reference, which is an expression. This one is a number literal, which is an expression. This one is a greater expression, which is a binary expression, which is, an expression. So basically, also this, well, it's the greater expression. So in order to use the expression facilities elsewhere, you probably want to make something an expression and then, use your own kinds of expressions by inheriting from expression. The interpreter, we can take a brief look, for example, at how the adding works. Oops. And so we go to the expression simple types interpreter. And we can scroll, for example, to the plus. And basically, the plus, if let's see, the plus if left and right side are both numbers without decimal dots, we just basically perform the addition. So basically this says the plus language concept. If the left child is an int and the right side is an int or a subtype thereof, then this is the code that runs. Now, if you forget about the stop, then this is basically a recursive call of the interpreter. Hash calls the interpreter again, evaluates the left side, evaluates the right side, and the add is the add from Java big integer, because the execution domain here on the right side is Java, and we represent the integers from KernelF as big ints from Java. And the reason why the system knows that this is a big integer is because there is a type mapping from KernelF int to Java big integer, which means that the system can know that if the left side is constrained to be a KernelF int, then if you evaluate it, you must get a big integer. So this way you can write very compact right sides. But the point is that the right side here is Java code. And so when we later write an interpreter for our state machine language, then we basically have to write Java code. And when we want to evaluate an expression, we basically just call hash into the interpreter world again. So I'm not going to talk much more about the KernelF structure. Again, look at this paper here if you want to learn the details and see the scope of the language. But what we'll need is basically the comparison operators and the ability to write number literals, and then we'll have to build a facility to refer to to variables, and you might not be surprised that this is another expression, varref, which is specifically built for the state machine language. All right, in the next video we'll actually look at the integration of the two.